Hello everyone. This is the introduction video for Lab 9, week 1. For this lab, we're going to talk about capacitors and inductors. So in previous lab, we already talked about capacitors, which is a device that stores electrical energy in an electric field. So we used capacitors in our rectifier circuits and also the operational amplifier circuits. And today's lab, we're gonna talk about another interesting properties of capacitors, which is the relationship between voltage and current in a capacitor. We're also gonna introduce inductors, which have many similarities to capacitors. So let's first recall the voltage-current relationship of a resistor, which is governed by the Ohm's law, where current is equal to voltage divided by resistance under both DC and AC circuits. So for a capacitor, in a DC circuit, a capacitor is considered as open, which means the current cannot go through the capacitor. But under an AC circuit, the current voltage following these equations, where current is equal to C, which is capacitance, times a derivative, which is dV over dt. So V is our voltage, T is the time. So how should we understand this equation? One intuition is this derivative measures the steepness of the graph of a function, which means the derivative is the slope of our voltage signal. So for example, if our voltage is increasing, then the slope is positive and our current is also positive. When the voltage is decreasing, the current is negative. When the voltage is constant and there is no slope, then our current is equal to 0. So that's how we understand this equation. One good example here is this triangle wave. So this signal has two types of slope, increasing slope and decreasing slope. So if we apply this voltage signal across our capacitor, and because of this equation, this voltage current relationship here, when the voltage is increasing, the current will be positive. When it's decreasing, current will be negative. So as a result, our current will become a square wave, looks like this. So you see, this is the interesting part of this property, because unlike resistors, the voltage and current they have to change together, they have to be in the same shape. But for capacitor, the voltage and current, they don't have to change together. They even don't have to be in the same shape. And this is because of this derivative term here. It gives the capacitor the ability to differentiate the signal. And this can be used in many other applications. But for this lab, all you need to remember is just this equation and how it affects the voltage and current relationship here. And we're also going to introduce the inductor here. Remember we said the inductor has some similarities to the capacitor. So the first similarity is an inductor is also a device that stores electrical energy, just like a capacitor, but in a magnetic field. And the second one, it has similar voltage and current relationship. So in a DC circuit, the inductor is considered as short or as a wire, but in an AC circuit, it is following this equation here. So we see this equation and these equations, they are pretty similar. The only difference is we swap the current and voltage terms in the equation and replace the capacitance with L, the inductance. So because of these similar equations As a result, the inductor has a very similar voltage current relationship or properties to the capacitor. So for this lab, we mainly focus on testing capacitor, and we mainly focus on this equation here.